Welcome back. In this video, I'm going to look at some applications of our models, in particular linear models, exponential models, logarithmic models, and quadratic models. So to start, I have a graph here which shows the population of adults 65 and over in the United States for years from 1900 up through 2020. The values for 2030, 40, and 50, those are predicted values. These are in millions. So in 1900, there were 3.1 million adults 65 and over. In 1950, there were 12.3 million, and so forth. So we're going to see if we can use this data to build a model. And I see that this is increasing as we move through the years, and I think that an exponential model is going to be appropriate here. Obviously, this would not continue. There doesn't really make sense for that in the previous years that we would have a huge population that decreased and went up, which would be the case for a quadratic. But this is going to start be small and then gradually increase and then start to get bigger faster. So I have taken the liberty of putting this data in my calculator. Let me move this up a little bit and turn this on. And in my stat list, so these are years. The first year was 1900, and then this is 10 years later and so forth. So these are years after 1899, basically. So this is 1 year after that. It was 3.1 million. So let's look at the exponential model. So I'll go back to my stat menu under calculations, scroll down to exponential regression. That's corresponds to the 0 there. And my data is in list 1 and list 2. And so the model is f of x equals, and I'm going to round to 3 decimal places, 3.47, and I'll have to round that up to 6. And then for the base of the exponential, I'll use 1.02, and I'll round this to a 3 to the power of x. So let's say that we want to make a prediction for the year 2000. So how many years after 1899 is this? So that would be 101 years after. So I'm going to basically evaluate my function at 101. So let's go back to my home screen, and I'll take 1.023, raise it to a power of 101. That evaluates to 9.94. I still need to multiply by 3.476 times 3.476. And I end up with 34, and we're going to round to 1 decimal place, 34.6 million. Now, in the actual graph from the year 2000, I'll slide that back over here. In 2000, the actual population of adults age 65 and older was 34.8. So 34.8 is the actual population. So there's a little bit of a difference here of about 0.2 million. So we're off by 0.2 million. That's the same as 200,000. So our prediction, in this case, underestimates the population by about 200,000. But that's not too shabby. Next, let's look at our model for the year, the prediction for the year 2030. So again, our base year is 1899. So at 101, that took us to the year 2000. I need to add 30 to that. So our x is going to equal 131. So I want to evaluate our function at 131. So I'll take 1.023, raise that to the power of 131, and then multiply it by 3.476. And we get a prediction of 68.5 2.4 million. That's, again, the prediction for the year 2030. Now, in the graphic here, for 2030, we had 70.3 million. So, we're off by more this time. Let's go back to our graph, and over top of this, I'm going to put our function in so that we can see both the function and the scatter plot. So I'll take 3.476 and then times 1.023 raised to the power of x. Close my parentheses. Let's do this again. So our model works really well, but at some point it looks like our model is increasing faster than the predictions according to the graphic. So the graphic seems to say this is going to, at some point, maybe start to level off a little bit. So the model works really well up to a point. And so when we were looking at 2030, that's this dot here, we're seeing that it's a little high, and then we would expect that our model would overshoot the estimates that were in the graphic for the years 2040 and 2050. So I'll stop for now, and in the next video I'll show you another application of these models.